How are you, ladies and gentlemen? I want to talk about angular motion, drives, and power. And this information is derived from the Fundamentals of Engineering Science book written by G.R. Titcomb, but also I've added my own explanations to make it easy to understand. It is important to understand angular motion, especially if you are dealing with machines. There is a relationship between angular motion and linear motion. Motion in cars, aeroplanes, conveyor belts, and many parts of factories, etc., starts in rotational movements in machines, motors, engines, shafts, etc., before proceeding to linear motion. There are two methods of defining angular motion. These are revolutions per minute and radians per second. It is a normal practice when dealing with the power of rotation in parts of machines such as motors, engines, etc., to designate the speeds using revolutions per minute, RPM. When a circular shaft rotates and makes one revolution, a distance traveled by a point on the periphery of the shaft is given by the formula S is equal to 2 pi r, where S is the distance moved in the periphery, r is the radius, and by so doing we will have made a rotation of 360 degrees. Defining a radian. One radian is defined to be equivalent to the angle subtended by an arc equal to the radius of a circle. So we've got here you can see the circle here. This is the radius outside, and inside there is angle theta. So the angle theta subtended by an arc equal to the radius r is called a radian. The angle subtended by an arc having a length L is equal to pi r is equal to 360. The angle subtended by an arc having a length r can be given by the formula based on the following proportion. That is the angle divided by the distance subtending that angle. You go theta over r is equal to 360 divided by 2 pi r. So you're making theta subject of theta is equal to 360 over 2 pi r. So theta is equal to 1/8 over pi, or it is approximately 57.3 degrees. So 1 radians is equivalent to 57.3 degrees. Distance traveled by a point on the circular periphery is the angle turned in radians times the radius of the arc, where theta is the angle in radians, s the distance traveled by a point on the periphery, and r is the radius. So velocity of a point on the circular periphery is equal to distance over time. So it is equal to theta times r divided by t. Theta over time is called omega, or the angular velocity in radians per second. So velocity of v is the velocity of point on the circular periphery, t is the time in seconds, and omega is the angular velocity in radians per second. Example, a shaft having a radius equal to 150 millimeters makes a rotation of 4 radians within 2 seconds. Compute the linear velocity of a point on the periphery of the arc in meters per second. So velocity is equal to theta times r over t is equal to omega times r is equal to 4 radians times 0.15 meters, which is the radius of the arc, divided by 2 seconds. So you've got 0.3 meters per second. Relationship between radians per second and revolutions per minute. If an object is rotated at n revolutions per minute, then the distance traveled in 1 minute is equal to 2 pi r times n. So it is the circumference times the number of rotation per minute. This distance, when working in radians per second, you have got is equal to radius times omega times 60. Radius times omega is the distance traveled in 1 second. So in 1 minute, you multiply by 60 to get that answer. So equation 1 and 2 are equal. So you can equate them. That S is equal to 2 pi Rn is equal to R omega 60. So omega is equal to 2 pi n over 60. That is the relationship between this distance, velocity in radians per second, and number of rotation in revolutions per minute. So N is the angular velocity in revolutions per minute. Omega is angular velocity in radians per second. Torque, work and power. Normally they compute torque in order to get power in when they are dealing with engines. Computation of torque. Here we got a force F acting on the radius at the circumference of an arc, and this force is acting at a distance r, or equal to radius from the center of the arc. So assume force F is acting at the tangent of a circle, and the circle rotates at an angle theta. The work done to move the force at a distance s, work is equal to force times this is equal to F times s. S is the distance, F is the force. But the distance is equal to radius times the angle in radians. So is equal to r times theta. Work is equal to force times r times theta. F times r is the moment of the tangential force about the center and is normally called torque, T. Therefore, replacing Fr with T, we get power is equal to, get that work is equal to tangent times theta is equal to T times theta. So therefore, we got power is equal to work over time is equal to tangent times theta over time. So the power is equal to tangent to torque times omega, and the omega is equal to 2 pi r theta. Therefore, relation between 2 power and revolution per minute is equal to power is equal to 2 pi t n, where n is angular velocity and revolution per minute and t is torque. The sources of torque. Sources of rotation may be engines, motors, manual work, etc. Tangential forces for sources of energy are transferred to other shafts by means of wires, belts, or gears. You can see here, these are belt drives. You've got a driving pulley and driven pulley, and then the driver pulley is driving the driven one by rotational movement. So one pulley is rotating and it transfers that rotation to the other pulley through belts. So, and if you can see the belt, there is the tight side and the slack side. Figure 5 shows one pulley which is transferring torque to another pulley. So it is driving the other pulley using torque from that belt. Rotation. And this is another type of pulley which is called a V pulley because it is V-shaped. So you can V-shaped. There is V belt. You can see the belt here. So, and you can have the belts now put in reverse side, as you can see here. You can drive a shaft by interchanging the belts. If you want those driver and driven to change, especially the driven one, to change the direction of rotation, you put the pulleys in X side, in a crossing side as shown in this diagram. Reverse. So this is a reverse belt, because in reverse direction on the driven pulley. Computation of torque in belts. So when you have two belts, you have a belt rotating, moving, be driven by one pulley and causing rotation on the other pulley. One side of the pulley is called the tight side, where the pulley is very tight, and the other side of the pulley normally is slack. It is not tight. So the actual force causing rotation on the driven pulley is the difference between the tension force on the tight side and the tension on the pulley side. It is the difference. So you can see the net force causing rotation on the shaft is the difference of the forces in the belt. You've got force 1 minus force 2. So the difference, you get the actual force acting on the pulley. So torque is equal to force times the radius. So it is equal to F1 minus F2 in bracket times the radius. And this is called torque, as you remember. Please bear in mind that power is computed by the equation below. Power is equal to torque times the angular velocity. Gears, the function of gears. So we discussed about pulleys, now we're discussing about gears. The function of gears is to change speed on rotating paths. Number 2, to change movement's direction on rotating paths, and to enable transfer of movements to sprockets. So you know that there are gears in cars, aeroplanes, and whatever, and that function is to change, speed of rotating parts of the engine, or to cause reverse movement on the engine. Calculating velocity ratios in gears. The following figure 9 indicates gears A and B connect to corresponding shafts. NA, you can see, is the number of teeth in the gear A, and NB is the number of teeth in gears B. RA is the number of rotations in gears on the shaft A, and RB are the number of rotation on shaft B. You can see the gears here. They are rotating, and if you check the rotation, you can find that they are rotating in opposite directions. The size of production teeth of gears and valves are normally the same width to facilitate smooth movement of the gears relative to one another. Unless there is slippage among the teeth, the total number of teeth moving on the gear wheel B is the same as those on gear wheel A. These gears are said to mesh with one another, and since every gear teeth for A mesh or move together with the corresponding gear teeth on B, the gear wheel B, which has less diameter and therefore have less number of gear wheels, will have to rotate faster to ensure meshing of the gear teeth. If there are RA rotations on the shaft A, the total of RA times NA, where are wheels rotating around for shaft B, the number of gear wheels rotating around is RB times NB. The cumulative number of rotating wheels will be the same, but the number of rotations will be different depending on the number of wheels on each wheel. So RA times NA is equal to RB times NB. Direction of rotation. If you check these gears, you can find that gear A is rotating in clockwise direction, but gears B are rotating in anti-clockwise direction. So if we want them to move in one direction, then we need to introduce what they call idle gear. So rearrange the equation to get rotation. We got RA times NA is equal to RB times NB. NA over NB is equal to RB over RB. Is equal to RB over RA. And these are called gear ratios. As noted, measured gears will be rotating in opposite directions. However, the engineer may wish to have rotating gears having a final motion in the same direction as the first. It is therefore the practice to introduce a gear in between to change the direction, and have gear C moving on the same direction as A. The gears B are called idler gears. Check here in figure 11, you will find gears A going in clockwise direction, and the gear B, gear B will be rotating in counterclockwise direction, but gear C now will be moving in the same direction as the gear A. So gears B are introduced to change the direction, and they are called idler gears. Another application of gears is chain and sprocket. You can see here now you've got chain and you've got some sprockets. You may find it in bicycles or even in bulldozers. So gears are also used to drive sprockets, as you can see in the diagram shown. Then this is chain and sprockets as shown in figure 13. So that is the function of gears.